Right now, at this exact moment, a radio signal weaker than a refrigerator light bulb is crawling across the dark toward a dish in the Australian desert. It left its source more than 23 hours ago. By the time you finish this sentence, it will still be traveling. That signal is coming from Voyager 1, a machine built in the 1970s, currently more than 25 billion kilometers from the room you're sitting in. Most people know Voyager 1 as the spacecraft that carries the golden record, humanity's mixtape to the cosmos, in case anyone out there ever finds it. That part of the story everyone knows. But there is a second Voyager 1 story, one that almost nobody has actually sat down and been told properly. It's the story of a machine that was supposed to die in the early 1980s, that instead crossed a boundary no human object had ever crossed. And then, on the other side of that boundary, found something that isn't supposed to be there. Not a planet, not a comet, a sound, a hum, in the emptiest place humans have ever measured, where there should be nothing at all to hum. And right now, in 2026, that same fragile spacecraft is in the middle of a slow-motion crisis that could end the whole mission within months. Stay with me, because by the end of this, you will not think about empty space the same way again. To understand why a nearly 50-year-old machine finding a hum in the void is such a big deal, you have to go back to where this thing started. Because the gap between what Voyager 1 was built for and what it actually became is one of the great accidents in the history of science. Voyager 1 launched on September 5th, 1977 from Cape Canaveral, Florida, riding a Titan Centaur rocket into the sky. Its job, on paper, was almost embarrassingly modest by today's standards. Fly past Jupiter, fly past Saturn, take some pictures, measure some magnetic fields, and call it a career. NASA budgeted the mission for about 5 years. 5 years for a machine that, as this is being narrated, has now been operating for over 48 years. That's the first thing you need to sit with. Designed to last 5 years. Still transmitting data across interstellar space 48 years later. Not a rounding error, a completely different mission than the one anyone signed up for. The reason Voyager 1 got the chance to become something bigger than its original job description comes down to an accident of orbital mechanics that happens roughly once every 176 years. In the late 1970s, Jupiter, Saturn, Uranus, and Neptune lined up on the same side of the solar system in a way that let a single spacecraft use each planet's gravity as a slingshot to reach the next one. Engineers called it the Grand Tour. Voyager 1 only took the Jupiter and Saturn legs of that tour, using Titan's atmosphere for a close pass that flung it up and out of the plane of the solar system entirely, away from the other planets, on a one-way trajectory toward the edge of everything the sun controls. And it kept going. On August 25th, 2012, Voyager 1 became the only spacecraft in history, out of every object humans have ever launched, to cross out of the sun's bubble of influence and into true interstellar space. The region between the stars, not a nearby moon, not the asteroid belt, the literal gap between our star and the next ones. As of today, it remains the single most distant human-made object that exists, more than 25 billion kilometers out and adding another roughly 17 kilometers of distance every single second. Its twin, Voyager 2, followed it out 6 years later in 2018, but Voyager 1 got there first, and Voyager 1 is the one whose instruments picked up the sound this story is really about. For a long time, nobody could even be certain the crossing had actually happened. Unlike flying past a planet, where you can literally photograph the moment of arrival, interstellar space doesn't announce itself with a visible landmark. The one instrument that could have measured the local plasma density directly and immediately, confirming the crossing on the spot, had already failed decades earlier, not long after the Saturn flyby in the early 1980s. So mission scientists had to wait, essentially, for the universe to hand them a lucky break. An eruption from the sun sent a wave of charged particles outward that eventually reached Voyager 1, and when it hit, it caused the surrounding plasma to oscillate at a very specific frequency. From that frequency, scientists could calculate the density of the plasma around the spacecraft. It came out remarkably close to the value theory predicted for true interstellar space, not the thinner solar wind. It took over a year of waiting and cross-checking after the actual crossing before NASA was confident enough to announce it publicly. That alone tells you something about how different this environment is from anything closer to home. There was no single dramatic threshold to point a camera at, only a patient, indirect, almost detective-like process of confirming that a machine had quietly slipped out of the only environment humans had ever directly measured. Here's the part that trips people up, so let's build it slowly. Picture the sun not as a still ball of light hanging in space, but as something closer to a fountain. It's constantly spraying out a stream of charged particles, called the solar wind, in every direction, at speeds of over 1 million miles an hour. That outward spray inflates a gigantic bubble around our entire solar system called the heliosphere. Think of the heliosphere as being like the bow wave a boat pushes ahead of itself in water, except instead of a boat cutting, Through a lake, it's our star cutting through the galaxy, and instead of one wave, it's a bubble roughly twice as wide as Pluto's orbit, sealing us off from most of the raw radiation and debris drifting between stars. But a fountain only sprays so far before gravity and pressure win. At some distance, the outward push of the solar wind runs out of strength, and it meets the resistance of the interstellar medium, the thin soup of gas, dust, and charged particles that fills the space between star systems, left over from other stars, other supernovae, other explosions across the galaxy. Where those two things meet and neither one wins outright, you get a boundary called the helopause. Scientists used to imagine it a little like the edge of a river meeting the sea, a place where you can point to a line, one side moving, one side still. Voyager 1 was sent out there specifically to find that line and cross it. It succeeded. What it found once it got there is where the impossible part of this story actually begins. Before Voyager 1 actually reached the helopause, the working model in most textbooks was fairly tidy. Scientists expected a boundary, expected a jump in plasma density as you crossed from the thin solar wind into the thicker interstellar medium, and expected that jump to look something like a wall. Clean transition, you could measure almost instantly, the astrophysical equivalent of walking from one room into another. The first surprise was that it didn't behave like a wall at all. When Voyager 1's plasma wave instrument started registering the crossing in 2013, mission scientists realized the transition wasn't a clean line, but a thick, structured, months-long region. Boston University astronomer Merav Ofer, who has spent years modeling this boundary, put it plainly afterward. The team had expected something like a quick blip, but the helopause turned out to be far thicker and more complicated than anyone had modeled. That was surprise number one. The edge of the solar system isn't an edge, it's a zone. Here's where the twist arrives, though, because a thick boundary alone wouldn't be that shocking. What actually stopped researchers cold was the temperature. As Voyager 1's instruments studied that thick, structured transition zone, they recorded blistering temperatures at the helopause, somewhere in the range of 30,000 to 50,000 Kelvin. For comparison, the surface of the Sun itself sits at around 5,800 Kelvin. Some researchers nicknamed the region a wall of fire. Even though it isn't fire in any way you or I would recognize, there simply aren't enough particles packed into that space for the heat to transfer the way it would in a candle flame or a stovetop, which is the only reason Voyager 1 wasn't cooked alive passing through it. Still, that number, tens of thousands of degrees, sitting at the supposed threshold of empty interstellar space, did not match the smooth, gradual, gently cooling boundary most models predicted. Explanation 1, a calm cooling gradient, was ruled out by the data almost immediately. So that idea was dropped, and researchers had to go looking for a messier answer. Turbulence, magnetic coupling, energy being dumped into the boundary in ways nobody had fully modeled before Voyager actually measured it directly. Now stop and sit with that for a second. A boundary tens of billions of kilometers from Earth, one that was supposed to be a quiet, gradual fade-out, turned out instead to be one of the most turbulent, energetic, and least understood regions Voyager has ever flown through. And it took an actual spacecraft physically punching through it to find that out, because no telescope on Earth, however powerful, can measure plasma density and temperature at that resolution from this far away. The second twist, and arguably the strangest one, showed up after Voyager 1 had already been sitting in interstellar space for years. Scientists had assumed the region beyond the helopause would be close to silent from a plasma wave perspective. Quiet, except for the occasional violent event, like a shock wave rippling outward from a solar eruption, slamming into the interstellar medium and briefly ringing it like a bell. Those shock-triggered plasma oscillation events were, for years, the only tool scientists had to estimate the density of interstellar space. And they only happened occasionally, whenever the sun sent out a strong enough disturbance to reach that far. Then, starting around 2017, Voyager 1's plasma wave instrument began picking up something nobody had planned for. A persistent, extremely faint, narrowband signal that didn't come from any solar shockwave at all. It didn't spike and fade like the shock events. It just kept going quietly, continuously for years as the spacecraft coasted onward. Cornell researcher Stella Koch-Ocker, who led the study identifying it, described it simply as a very faint monotone signal in a narrow frequency band, and called it, in her own words, the persistent hum of interstellar gas. A hum. In the space between the stars, a region most people imagine as the emptiest, most silent place imaginable, Voyager 1 found something that behaves almost like background noise that never stops. Explanation 1 for this, that it was just leftover shock activity from an old solar event, didn't hold up because the signal persisted steadily for years with no matching shock event to explain it. So that idea got dropped too. Researchers now suspect it may come from tiny thermal fluctuations in the interstellar plasma itself, something like the gas gently vibrating on its own. But they'll tell you directly that they don't fully know yet. Think about what that actually means practically. For the first time, scientists had a way to measure the density of interstellar plasma continuously, in something close to real time, over stretches of billions of kilometers, instead of waiting years between rare shock events to get a single data point. That persistent hum turned Voyager 1, almost by accident, into a continuously broadcasting instrument for mapping the density and turbulence of the material between the stars, at a resolution nobody had access to before. And there was a third twist layered on top of the first two, one that came from a completely different instrument. Once Voyager 1 crossed the heliopause, its cosmic ray detectors picked up an odd, lopsided pattern in the high-energy particles arriving from deep space, called an anisotropy, meaning the particles weren't arriving evenly from all directions, the way you'd expect in truly open interstellar space. Instead, there was a directional bias tied to the surrounding magnetic field, one that current models of the heliosphere's shape and the local interstellar magnetic field still struggle to fully explain. Combined with earlier findings that some particles seem to leak back and forth across the heliopause rather than being cleanly stopped by it, the boundary looks less like a sealed hull and more like a semi-permeable membrane, letting certain things through in both directions, under conditions scientists are still working out. Put those three findings together: a boundary that's a thick, turbulent zone instead of a clean line, temperatures in the tens of thousands of degrees where a gentle fade was expected, and a persistent, unexplained hum layered with a lopsided cosmic ray pattern nobody predicted. And you get a heliopause that behaves nothing like the textbook diagram most of us grew up with. Not a wall, not a curtain, a living, turbulent, leaky frontier that an entire generation of astrophysics had to be rewritten around, using data from one aging spacecraft that was never even designed to make these particular measurements in the first place. This isn't a footnote you can tuck into an appendix somewhere. This is the kind of finding that forces an entire field to go back and reconsider its starting assumptions. For decades, the heliopause was treated in models as essentially a boundary condition, a tidy edge you could draw on a diagram and move on from. Voyager 1's data means that boundary condition has to be replaced with something dynamic, turbulent, temperature spiking, permeable in ways that still aren't fully mapped. And because the heliosphere is essentially Earth's radiation shield against the wider galaxy, deflecting a huge share of high-energy cosmic rays that would otherwise reach the inner solar system, understanding exactly how strong, how leaky, and how stable that shield really is isn't just an academic curiosity. It's directly tied to how much cosmic radiation reaches Earth's environment over long timescales, which matters for everything from the history of Earth's atmosphere to the radiation risk faced by future astronauts traveling beyond it. There's a bigger implication, too. Every sun-like star is thought to blow its own version of a heliosphere, its own protective bubble pushed out into the galaxy. If our own heliopause turns out to be this turbulent, this leaky, and this poorly predicted by prior models, then the astrospheres surrounding other stars, including stars with potentially habitable planets, probably don't look like the clean bubbles in old textbook diagrams either. Voyager 1's data is quietly becoming a foundational reference point for scientists trying to model how other stars shield, or fail to shield, their own planets from the harsher galactic environment beyond. One aging probe, sent to check a box near Jupiter and Saturn in 1977, ended up rewriting a piece of stellar astrophysics that applies to star systems it will never come anywhere close to visiting. It also changes how scientists think about the history of our own solar system. If the boundary that shields us from interstellar radiation isn't a fixed, static wall, but something that flexes, thins, and thickens over time as the sun's own activity rises and falls, then the amount of cosmic radiation reaching the inner solar system, including Earth, hasn't been constant throughout our planet's history either. Some researchers now suspect that past compressions or expansions of the heliosphere, driven by the sun, passing through denser or thinner patches of the interstellar medium over millions of years, could have subtly influenced Earth's climate and radiation environment in ways that are only now becoming testable, thanks largely to the ground truth data Voyager 1 provided from actually being out there. None of that was part of the mission's original justification to Congress in the 1970s. It's a byproduct of a spacecraft that simply refused to stop working long after anyone expected it to. But here's the part that makes this story urgent right now in 2026, rather than just a historical curiosity. The machine that made all of this possible is dying, on a timeline measured in years, not decades. And the team keeping it alive is running out of tricks. Voyager 1 doesn't run on solar panels, because at this distance, the sun is just another bright star in the sky, far too dim to power anything. Instead, it runs on a radioisotope thermoelectric generator, a device that converts the heat given off by decaying plutonium into electricity. That heat source cools a little every single year, no matter what anyone on Earth does about it. And the spacecraft loses roughly 4 watts of usable power annually. 4. Watts sounds trivial, less than a nightlight. On Voyager 1, after 48 years of that steady bleed, 4 watts is the difference between running an instrument and shutting it off forever. So the mission team has been forced into a long, deliberate triage. Of the 10 original science instrument packages the 2 Voyagers carried, most have already been switched off, one at a time, to keep the spacecraft's most essential systems alive. Voyager 1's cosmic ray subsystem went dark on February 25, 2025. Its low-energy charged particles experiment, the instrument that helped characterize that cosmic ray anisotropy we just talked about, was shut down on April 17, 2026. As of right now, only 2 science instruments remain switched on aboard Voyager 1, the magnetometer and the plasma wave subsystem, the very instrument that first picked up that mysterious interstellar hum. Everything now depends on squeezing every remaining watt toward keeping those 2 alive as long as physically possible. Power isn't even the only threat. In 2025, the mission faced a genuine no-second-chances crisis involving the spacecraft's thrusters, the small jets that make tiny adjustments to keep Voyager 1's antenna aimed at Earth with extreme precision. At a distance of over 25 billion kilometers, the margin for error is almost non-existent. A pointing mistake of roughly half a degree would swing the radio beam off target by a distance comparable to the gap between the Earth and the Sun, and the connection would simply be gone, with no way for anyone to nudge it back into alignment. Voyager 1's original primary roll thrusters had been declared dead back in 2004 after 2 small internal heaters lost power, leaving the spacecraft dependent ever since on a backup set. By 2025, that backup set had started developing its own problem, a fuel tube gradually clogging with residue shed by an aging rubber component inside the fuel tank, an opening that had narrowed from about 1/4 of a millimeter down to roughly 35 microns, about half the width of a single human hair. Facing the possibility of losing the ability to point the antenna at all, engineers at NASA's Jet Propulsion Laboratory went back to the thrusters everyone had written off 2 decades earlier, suspecting the 2004 failure hadn't been a mechanical death at all, but a stuck switch in the power circuit feeding the heaters. The fix carried real risk. If the long-dormant thrusters ever fired automatically, as the spacecraft's own safety programming would trigger, if it drifted off its guide star, before the heaters had been properly restarted, the result could have been a small explosion aboard the most distant working spacecraft ever built. And the team was racing a hard deadline because on May 4th, 2025, the one Deep Space Network antenna powerful enough to send commands to Voyager 1, a giant 70-meter dish in Canberra, Australia, was scheduled to go completely offline for months of upgrades, with only brief windows of operation in August and December. On March 20th, 2025, the team sent the command sequence and waited through the round-trip delay for the return telemetry. Within about 20 minutes of relevant data coming back, the temperature readings on the old thruster heaters rose sharply. The thrusters, once considered dead for 21 years, had come back online. Todd Barber, the mission's propulsion lead at JPL, described the moment afterward as a glorious one for the team, and called it, in his words, yet another miracle, save for Voyager. Best case, that revived backup buys the mission years of additional redundancy for pointing the antenna. Worst case, if both thruster sets eventually clog or fail entirely, the spacecraft loses its ability to keep its antenna aimed at Earth, and a machine with a still functioning radio, a still decaying power source, and still live instruments simply goes silent forever because there is no way to send a repair crew 25 billion kilometers into interstellar space. As former Voyager project manager John Cassani once put it, the engineers never designed these spacecraft to last 30 or 40 years. They designed them not to fail. Whether that design philosophy holds for a few more years is now an open question nobody can answer with certainty. Even with all of this, Voyager 1 has left behind more open questions than answers. Scientists still don't know exactly what generates that persistent interstellar hum. Whether it comes from thermal fluctuations in the plasma itself or some other process nobody has fully modeled yet. They don't know why the helopause appears noticeably different in shape and behavior between where Voyager 1 crossed it and where Voyager 2 crossed it 6 years later. A discrepancy that current models of the heliosphere's overall shape still can't fully resolve. They don't fully understand the mechanism behind that lopsided cosmic ray pattern, or exactly how particles manage to leak across a boundary that was once assumed to seal cleanly in one direction. And there is, right now, no funded, built, or launched successor mission specifically designed to keep collecting this kind of data once Voyager 1 finally goes quiet. NASA and Johns Hopkins Applied Physics Laboratory have studied concepts for a dedicated interstellar probe, a spacecraft built from the ground up to study this exact environment with modern instruments. But as of today, that mission exists only on paper, without a funding line or a launch date. When Voyager 1's last instrument switches off, humanity's only continuous, in-place sensor in interstellar space goes with it, and there's nothing currently under construction to replace it. Before we zoom all the way out, it's worth just letting the sheer scale of what this machine has done wash over you for a moment, rapid fire. Voyager 1 remains the single most distant human-made object in existence. It is the only spacecraft ever to have transmitted data from true interstellar space. It's currently moving at roughly 61,000 kilometers per hour relative to the Sun. On November 18th, 2026, it's projected to cross the threshold of one full light day from Earth, meaning a signal will need a full 24 hours just to make the one-way trip home. It carries the golden record, etched with sounds, images, and greetings in dozens of languages, meant for absolutely nobody in particular, and absolutely anybody who might one day find it. It has already survived onboard computer faults, a mysterious data format glitch in 2023 that briefly cut off comprehensible communication entirely, and years of thruster degradation. Its own team has revived thrusters considered dead for over 2 decades. If nothing intervenes, in roughly 300 years, it will reach the outer edge of the theorized Oort cloud, and it will take about 30,000 years just to pass all the way through it. In around 40,000 years, with no course correction and no destination in mind, it will drift within about 1.6 light years of a star called Gliese 445. It carries instruments built with 1970s engineering that are still today generating publishable scientific discoveries. Almost none of that was in the original job description. Step back from all the numbers for a second, because underneath the plasma density readings and the thruster telemetry, there's something quieter going on here. A machine humans built to look at 2 planets up close ended up traveling so far past its own assignment that it walked straight into the boundary between our star and the rest of the galaxy. And it found that boundary wasn't calm. It was turbulent. It was hot. It hummed. In a universe that so much of our imagination pictures as cold, silent, and empty once you leave the neighborhood of a star, Voyager 1 discovered a background hum that never stops, a kind of ambient breathing at the edge of everything we can call home. Still transmitting, 48 years and 25 billion kilometers later. Still measuring, with 2 working instruments where there used to be 10. Still listening for a hum humans didn't even know to expect until Voyager was already standing in the middle of it. That radio signal we started with, the one crawling toward that dish in Australia right now, carrying data from a place literally between the stars, it is still on its way right now as you hear this. If you want to be there for the next chapter, mark November 18th, 2026 on your calendar, because that's the day Voyager 1 is expected to cross one full light day from Earth, a threshold no human-made object has ever reached before, and mission engineers will be watching the power margins and the antenna pointing just as closely as they have been all year. Subscribe and turn on notifications if you want to know the moment there's real news, whether that's another instrument shutdown, another thruster crisis, or, if we're lucky, another discovery nobody predicted. This channel covers the real science, sourced from actual mission updates and published research, without inventing anything the data didn't show. If you have questions about what Voyager 1 might find next, or thoughts on what that interstellar hum might actually be, drop them below, and share this with someone who still thinks empty space means silent. Because right now, in a place colder and darker than almost anywhere in human experience, something is still humming. And a machine we built in 1977 running on decaying plutonium, aimed by thrusters engineers once wrote off as dead, is the only reason we know that at all.